Hello students, I hope all of you are doing well. So in this video we will be revising Newton's laws of motion, right? All the topics, all the concepts, we will be going through them one by one. Let us start. Yeah. So the topics that we will be covering in this video is some common forces, then your static equilibrium. We'll talk about unbalanced forces, which is basically application of F net equals to ma. Then pulley block system, we'll take some cases for pulley block system, weighing machine, spring balance, combination of springs, and finally pseudo force, right? So let us start. First is our common forces. Which common forces we use in NLM? The first one, if I start with, is your gravitational force, right? Gravitational force. Second one, if I talk about, it is your normal force. Normal force. Third is tension force. And fourth is your friction force. One by one, let us take a look at all of them. So, gravitational force. Gravitational force is any object of mass m will experience a gravitational force mg in vertically downward direction. So, gravitational force, which is also the weight, of the body. If I take some cases, right now, let's discuss gravitational force. So, in gravitational force, let's take some cases. A block of mass m which is kept on a surface, it will experience a gravitational force mg in vertically downward direction. Gravitational force is always vertically downward towards the center of earth, and the magnitude is mg, right? Next, if I take a look, let's suppose a block of mass m is kept on a wedge. It is kept on a wedge on an inclined plane having inclination angle theta. It will also experience vertically downward mg. Mg is vertically downward. Yes, in this case, we resolve this mg into two components. Component perpendicular to the incline and along the incline. Because the motion of the block will happen along the incline, therefore we find out forces along incline and perpendicular to incline. So if this angle is theta, then the two components comes out to be mg cos theta and this one is mg sin theta. So actually mg sin theta is the force which mg sin theta, the component of mg, is responsible for the motion of the block on the incline. Third, if I take a look, let's suppose a block of mass m is hanging with the help of a string. It will also experience a force, gravitational force of magnitude mg in vertically downward direction. Fine. These are some of the cases of mg. Next, if we take a look at normal force, let us see normal force. So, normal force. What is normal force? Normal force, it is a contact force which acts perpendicular to the contact surface. It is contact force acts perpendicular to contact surface, right? It is always pushing in nature. The two bodies which are in contact with each other, they always push. It is pushing in nature. It is a pushing force. Normal force is always a pushing force. Let me take some cases. So first, identical, if I take a look at this one, let's suppose a block of mass m is kept on the ground. Now, where is the contact? There is a contact between block and the ground surface. This is a contact. So because it is in contact, a normal force will come which will be perpendicular to contact surface and ground will be pushing it. So it will be perpendicular and upward direction, right? Now over here I want to discuss one point, that many students keep this confusion in mind, that this mg and normal are action reaction pair of each other. No, please don't have that confusion. The action mg and normal are not action reaction pair. Ground is applying normal on the block, so the reaction of this is block will apply normal on the ground. Block will apply normal on the ground in downward direction, which will be normal n only. Because according to your Newton's third law, action and reaction pair, they act on two different bodies. They are of same nature. Mg and normal are two different nature forces. So over here, I'll draw it more clearly if we draw the FBD for your ground, so the reaction of this normal will be reaction on the ground only, which will be pushing in nature, that is in downward direction, and its magnitude will be equals to n, right? Fine. Let us take a look this example, the incline example. If I take it, let's say this angle is theta, block of mass m is kept on it, right? How many contact surfaces are there? Two contact between the block and the wedge is in contact with the ground. So two normals, if I say, let's say that ground is applying n1 on this one, right? There is a force between block and the wedge which will be n2, right? Let us name, because this one we have named n1, so let's name n2, and n2 will be perpendicular to the contact surface. This is n2. Block will apply on the wedge which will be over here, this, right? n2. So this is about your normal force. One more example we can take a look. Let's say a sphere is placed in between two inclined surfaces. A sphere is placed in between two inclined surfaces. Then where will be the normal force? Normal is always perpendicular, so it will be n1 and n2. And these normal, because they are perpendicular to the inclined surface as well as they will be perpendicular to the sphere, the surface at this point, therefore these normal will be passing through the center of the sphere, right? So these are the cases for your normal. Let us look at the next, which is your tension. So next we will be discussing about tension, right? Let us see. If we talk about tension, it is a pulling force. It's a pulling force which acts in a string. Acts in a string when it is tight. When it is tight, right? When the string at both the ends is tight, it experiences a force which we call as tension. Let us take a look at some examples. So let's say a block of mass m is hanging with the help of a string. A block of mass m is hanging with the help of a string. So over here, tension force. Tension is always away from the joint because it is a pulling force. So over here, this is our joint. Tension will be in upward direction, T. Also, tension is, this string is connected with the ceiling. So tension over here will be in downward direction. Now you will notice one thing, that here also I have used T, here also I have used T. Because in NLM we take massless strings. In NLM, unless mentioned to us, we consider massless strings, and in massless string tension is same throughout. So over here, massless, so tension same. Fine. Let us take another example. Let's say two blocks M1 and M2 connected with the help of two different strings. So over here, if I say tension is T1, here also tension on the ceiling will be T1 only, but this one is other string. So here if I say tension, it will be downward. From the joint, tension is always a pulling force. So at this point, the string will pull it down. So it will be T2, and at this point away from the joint, it's a pulling force. So it will be T2 in upward direction, right? Let's take another example. Let's say a string is passing over a pulley and it is supporting two blocks, M2 and M1. M2 and M1, right? So over here, it's a single string. Tension on this M2 will be upward over here, and on M1 it will be T over here, right? So these are some of the cases of your tension force. Now, if we talk about the fourth one, which is your friction force. Friction force again is a contact force. Friction force again is a contact force which acts along the surface whenever there is tendency of motion or there is some relative motion, right? Now in NLM, when we consider your smooth surfaces, friction is not involved. Right now I have just described it. We will take friction in detail in the next video itself, right? So we are done with our some common forces. Now we will move on to our next topic, which is your static equilibrium. Let us look at it. So next we are discussing your static equilibrium. Let us see. So static equilibrium. What do we understand by static equilibrium? Static equilibrium is when the body is at rest. In general, what is the condition of equilibrium? Condition of equilibrium is F net is equals to 0. Whenever the summation of forces on a body is 0, we say that your body is in equilibrium, and when it is rest, it is static equilibrium, right? F net equals to 0. We also say that F net equals 0, that means forces are balanced. Now, let us take a look. One thing we need to be careful is that whenever we apply F net equals to 0, we always apply in X direction and Y direction separately. What I mean by this is that we F net equals to 0, but we write down forces in X direction and forces in Y direction equation separately, right? Let us understand this with the help of an example. Let's say that we have a situation in which, so a block of mass m is hanging with the help of a string. This string is being supported by two another strings. If it is hanging, it is at rest, that means it is in equilibrium. Let us apply the condition. First of all, let's draw the FBD. If we draw the FBD, on this mg will be acting downward. Let's say T, that is in this string tension I am terming as T. So at this joint T will be downward. In this string tension is T1. In this string tension is T2. This strings makes an angle of theta1 and theta2 with the ceiling. Fine. If we have to apply your F net equals to 0, first of all on the block. On the block, what can we write down? Now forces on the block are acting in Y direction. So if we apply F net equals to 0 specifically in Y direction, it will come out T minus mg is equals to 0. This is our first equation. Now let us apply your F net equals to 0 at this junction where three strings are meeting together, right? So over here these three strings are there. Now you will notice that this T1 and T2 are acting at certain angles. They are acting at certain angles. So our first step should be to resolve them into X direction and Y direction. Let us see. So if we see carefully, this is theta1, so this angle will also be theta1. This is theta2, so this angle will also be theta2. T is acting downward. This is T1. What is the component of T1 in X direction? We can take it as T1 cos theta1. In Y direction, it will be T1 sin theta1. Component of T2 in X and Y direction, it will be in X it will be T2 cos theta2. In Y direction, it will be T2 sin theta2. Right? Once we have resolved forces in X and Y, now let us apply your F net equals to 0 in X and Y separately. In X direction, what can we write for this? We can write down T1 cos theta1 minus T2 cos theta2 is equals to 0. In Y direction, we can write down downward force is T, this T over here which is acting downward. T, this is downward, so we will write it T1 sin theta1 plus T2 sin theta2 minus T is equals to 0. Equation number 2, equation number 3, right? We have got three variables T, which relation we already got, T minus mg equals to 0. From this we get tension is equals to mg. We can substitute here T as mg, T1 and T2, two variables are there, two equations are there, we can solve them, right? But more importantly, what we have, whenever we have forces, first of all we resolve them in X and Y direction and then apply Fx equals to 0 and Fy equals to 0 for static equilibrium condition, right? Now, this is one method that I have discussed with you. There is one more method to deal with this type of problem when three balanced forces are involved, which the method we term as your Lami's theorem. So, what I am talking about is, let's say three forces are there, your T, T1 and T2, T1 and T2. This only if I take a look, and let's say that over here this force is T1, the angle opposite to this, that means basically angle between T and T2 is alpha. The angle opposite to T2, beta, which is between T and T1 is beta, and angle opposite to T is your gamma. Then what Lami's theorem says is that whenever three forces are acting such that they are balanced, that means F net is equals to 0, then we can write down T1 by sine alpha is equals to T2 by sine beta is equals to T by sine gamma, right? That is the ratio of force by sine of the opposite angle will be constant. Using this Lami's theorem also we can solve whenever three balanced forces are involved, right? So this is all about your static equilibrium. Let us move ahead and take a look at your unbalanced forces. What do I mean by unbalanced forces? Unbalanced forces is when F net is not equals to 0. Unbalanced forces is when F net is not equals to 0, and if F net is not equals to 0, that implies we will apply our Newton's second law, which is F net is equals to MA. F net is equals to MA, right? Let us take a look at it in detail. Okay, next we are discussing your unbalanced forces. Unbalanced forces. What are unbalanced forces? When your F net is not equals to 0. F net is not equals to 0, then we'll have to consider your F net is equals to MA. F net is equals to MA. Newton's second law, force net is equals to mass into acceleration. Now here also I'll say the same thing what I discussed earlier, that to apply F net equals to MA, we use this in x direction and y direction separately. Let's consider a situation. Let's say a block of mass m is there, and on this multiple forces are acting, F1, F2, F3 and F4, right? Now over here, when we have to apply your F net equals to MA, we must resolve all the forces in x direction and y direction, and then apply Fx equals to MAX and Fy equals to MAY. That means in x direction and y direction separately, right? Now all the questions of your pulley block system, whenever the blocks or the system is moving, we use F equals to MA to solve them, right? Now one more thing that I want to discuss is about considering system. Different blocks are given, considering all of them as a single system. So let's consider a situation that 3 blocks are given to us, M1, M2 and M3, and a force F is applied on them, Now as we know that M1, M2, M3, all the 3 blocks will be moving with same acceleration. They will be moving because they are constrained to move. They have to move together only because force F is applying over here. They'll move together over here with same acceleration. Whenever all the particles, all the bodies of a system are moving with same acceleration, then we can directly use F is equals to M. We can consider all of these as part of single system and apply F equals to MA directly on whole. So F is equals to M. F is equals to M1 plus M2 plus M3 into A. With this we can find out either if they are asking acceleration or force, we can find out. I'll take more example to illustrate this point. Let's suppose a situation is given to you. Right? Let's say a block of mass M is kept on a wedge, a movable wedge. It is kept on a movable wedge of mass capital M, right? And a force F is acting on them. And it is mentioned to us in the question. Just a minute. Yeah, sorry. Let us continue. So what I was saying is that a block of mass M is kept on a wedge of mass, movable wedge of mass capital M, and a force F is acting on it. And in the question it is mentioned to you that the system moves together. That means the small m is at rest with respect to capital M. Small m is at rest with respect to capital M. That means both of them are having same acceleration A. Now in this case you can apply directly F is equals to, in x direction, capital M plus small m into A, right? This is force is equals to total mass of the system into acceleration, when each block, each body of the system is having same acceleration. If I take same example but a different situation is given to us. Let's say it is given to us that a block of mass small m is there, right? It is sliding down on the wedge, this wedge of mass capital M, angle is theta. Now this small block is sliding down with an acceleration of A2 and the wedge is moving with A1 over here. The wedge moves with A1 and the block moves down with A2 over here. Now both of them are having some different acceleration. They are not moving together. So we can't use this whole as a system over here. We will have to apply F equals to ma individually. For example, let's suppose this angle is theta. So for this one, if we resolve the forces, this angle will also be theta. So this angle is theta. So this acceleration components in x and y, what we'll get it over here, this will come out to be A2 cos theta, and this y direction will be A2 sin theta. So our acceleration of small m in x direction, we can write it as A1 minus A2 cos theta, and acceleration in y direction will be A2 sin theta. We will use forces F equals to ma on this wedge separately and on the block separately in x and y direction, right? Fine. Let us move ahead and let us look at application of F net equals to ma on pulley block system. Different cases we will take for pulley block system, right? Okay. So let us look at pulley block system. Pulley block system. Now over here, first of all, let us look at pulley. If we discuss in NLM, we consider ideal pulley. In NLM, we consider ideal pulley. What we mean by ideal pulley? Ideal pulley is massless and smooth. Massless and smooth. No friction is involved. Now, if it is an ideal pulley, if it's a massless, the strings will be applying two forces. The strings will be applying forces T here on this side. If let's say a string is passing over a pulley, and thus it will apply tension and tension. So as it is massless pulley, for massless pulley, if T and T is acting downward, the upward force must be equals to 2T, because forces on it should be balanced. On a massless pulley, F net equals to M0. So F net equals to 0. Therefore, this is T and T. So upward force will be 2T. First thing, this is something that we need to keep in mind. Another relation for movable pulleys you can keep in mind is, for movable pulley, let's say that a pulley is having a acceleration of AP, right, upward, and these two ends are having acceleration A1 and A2. These two ends are having acceleration A1 and A2. Then we can write the result. Acceleration of pulley is equals to A1 plus A2 by 2. A1 plus A2 by 2. Using constraint, we get this relation, that is acceleration of pulley equals to A1 plus A2 by 2. You will notice that I have used vector sign over here, as it may happen that one of them may be going up, down. That means you have to consider, while applying this relation, you should consider the sign also, right? Now, let us look at some of the basic cases of your pulley block system. So if we say two blocks M1 and M2 connected with a string which passes over a pulley, and let's say M2 is greater than M1, considering M2 is greater than M1, all the forces which are acting on it, FBD, if we draw the FBD, M2G will be downward, tension will be upward on the pulley, T will be over here down. For this, in the string, tension downward. On the hinge, on the support, the force will be 2T. T and T we have already discussed. Upward support, it will be 2T. Anyways, it is not moving, so it is fixed, but the force will be 2T. Okay. Next, over here on block M1G and tension upward. If M2 is heavier than M1, that means M2 will be moving down with the acceleration of A, and this will move up with the acceleration of A. If we apply F net equals to MA on the blocks individually, on this block we can write down, on this block, if we write the equation, M2G minus T is equals to M2A, right? Equation 1. On block M1, if we write down the equation, T minus M1G is equals to M1A, equation number 2. When we solve these two equations, the results that we get is two quantities that we calculate in these type of cases is your tension and the acceleration. So tension result we get is 2 M1 M2G by M1 plus M2, and acceleration result is M2 minus M1G by M1 plus M2. M2 is the heavier one, m2 minus m1g by m1 plus m2. Now these are two standard results for this pulley block system, which we also term as Atwood machine. So for this pulley block system, these are two standard results. You can keep them in mind. Let us look at some more cases of pulley block system. Yeah. So the situation I have considered is two blocks M1 and M2 connected with a string passing over a pulley which is connected on a wedge, on a fixed wedge, right? Now over here, if we draw the FBD, what all forces will be there? M1G will act down over here, tension on the block upward, T on the pulley, T on the pulley, then tension on M2, and on this M2, that is second block, it will be M2G sine theta, normal which is perpendicular to the incline, and M2G cos theta, right? Over here, which block will be moving down? It will be determined by the value of M1G and M2G sine theta, right? Which block will be moving down, which will be determined by M1G and M2G sine theta. Considering that, let's say M1 is going down. So what equations we can write down? On this block, if we write down the equation, it will come out M1G minus T is equals to M1 into A. Acceleration over here is downward. Fine. Next, on this, if we write down the equation, it will be along the incline because this block is moving along the incline. So forces, if we write down along the incline, it will be T minus M2G sine theta is equals to M2 into A. This is our second equation, right? Using this, we can find out tension and acceleration. Now, perpendicular to the incline, if we see what we are having perpendicular to incline, M2 is in rest. That implies normal will be equals to M2G cos theta, right? This is application of F net equals to MA in this situation. One more case we will take a look. Now, the case that I have considered over here is we have two blocks M1 and M2 which are connected with the help of two pulleys. One pulley is fixed, another pulley is movable, right? Let us draw the FBD first of all. So for this M1, over here tension will be acting, normal will be up, and M1G will be down. Normal and M1G are over here vertical, so they don't play any role in the motion of M1G, right? So only tension is responsible for its motion. Then over here on the pulley, if we draw the forces, T will be up, over here T, because this single string is there, tension and tension, T and T. If here it is T, it's a massless pulley, that implies over here tension should be 2T, right? On the block, I can draw it. This is your M2. So here it is 2T, that implies this string also has tension 2T. Downward it will be your M2G, right? Let us write down your F net equals to MA on both the blocks one by one. So over here, what can we write it? M2G minus 2T is equals to M2 into A2. That is the acceleration of second block, A2, right? Next, for this block, if we have to write down, it will be your T is equals to M1 into A1. A1 is the acceleration of, because they are connected with a movable pulley, that means they are not connected directly, they will not have same acceleration. This one I have taken A2, this one I have taken as A1. Now, how many variables we have? Considering masses are given, so T is the variable, and then your A1 and A2, three variables are there, but we have two equations, right? So we need one more equation, relation between A1 and A2. So earlier we have seen this is a movable pulley. So if you notice, this end is having how much acceleration? A1. This end will be having acceleration A1. This end is connected with a ceiling which is fixed. That means this end will be having over here zero acceleration. So the relation that we get, if we apply AP is equals to A1 plus A2 by 2. If we apply this relation, this A2 value will be coming out to be A1 by 2, right? This is A1, this end is having zero acceleration over here. So A2 is A1 by 2. We got first, second and third equation, three equations and three variables. Using them, we can calculate A1, A2 acceleration and tension, right? So this is all about your pulley block system. Now let us move on to the further topics. Now, next we are discussing is weighing machine. So let us consider a person is standing on top of a weighing machine, right? A person of mass M is standing. Now, what is the concept of weighing machine? What does weighing machine actually measures? So, weighing machine, when we are standing on weighing machine, we are applying a force. Basically, there is a normal force because we are in contact with the weighing machine. There is a normal force acting. This machine will apply normal upward on the person. Mg will be acting downward, and this person will apply normal on the weighing machine. So there is a normal on the weighing machine. Weighing machine is actually measuring this normal on, which is acting on it. How much is our normal over here? If you see for this person, if we look at FBD, normal value is equals to mg. Now this machine is measuring normal, but weighing machines are actually calibrated to give us the reading. Reading of weighing machine is N by G. Reading of weighing machines are N by G. That means weighing machines are calibrated to give the value by dividing it with G. So over here, how much we have? N is normal is mg divided by G. So we'll get it our reading as M. Right. Now let us consider some different cases. Let's suppose that weighing machine is kept in a lift which is moving up with some acceleration A. So let's say weighing machine is kept in a lift which is moving up with some acceleration A. Now in this case, if we look at the FBD of the person, what all forces will be acting? Normal will be upward, mg will be downward. But now N is not equals to mg. What is the equation that is forming? N minus mg is equals to ma. This is I am applying F equals to ma on the person. N minus mg is equals to ma. So normal value comes out. Normal is mg plus ma. In this case, what will be our reading? Reading of the weighing machine will be m g plus a by g. This will be the reading, right? Over here, if you notice the weight or the over here, the reading is more as compared to when the person is stationary. If I consider another case, let's suppose the lift is going down with the acceleration of a, and person is standing on the weighing machine which is present inside the lift, which is going down with acceleration A. If we look at forces, normal will be upward, mg will be downward. In this case, if we write down the force equation, it will be mg minus n is equals to ma. Normal value comes out how much? Normal is mg minus ma. So what will be the reading of the weighing machine? Reading of weighing machine will be m of g minus a by G. This is the reading of weighing machine. Now if you will notice carefully, in this case, when it is going up, the reading increases. That means the weight, the person will appear heavier, whereas when the lift is going down, the person will appear lighter. This is what happens if you have gone, when we visit our amusement park, over there when the ride is going upward, we feel heavier, whereas when the ride is going down, we feel lighter, right? In this case, if let's suppose I am talking about this specific case, let's suppose the acceleration of the lift becomes g only. If acceleration of the lift becomes equals to g, then what we will get? G minus g, it becomes 0. So reading will come out to be 0. That implies this is a case of weightlessness. So whenever your normal becomes 0, this is the condition of your weightlessness, right? So three different cases we have discussed. When the person is on a weighing machine which is stationary, when it is in a lift which is moving up with acceleration, when it is moving down with acceleration, right? So let us look ahead with spring balance. Spring balance is also identical, only same situation. Let's take a look at it. Okay, spring balance. Let us talk about spring balance. So spring balance, what does spring balance actually measure? Spring balance will measure the tension force experienced by the hook. Whenever we keep a block on the spring balance, because of the mg force, it will pull down the spring, and after some time the spring force will balance the mg force, spring force will balance the downward force. At that equilibrium position, whatever tension is experienced at the hook, that is what is measured by your spring balance. Now over here, if we take a look, tension will be upward, mg will be downward. If this is spring balance which is hung on a ceiling, so what will we get it? T will be equals to mg. But spring balance are calibrated, again they are calibrated over here, the reading that we get, they are calibrated to give us the reading by dividing it with g. So what value we will be getting? The reading will be mg by g, which is your m. Fine. Now I have taken, so this is our basic of your spring balance. Now I have taken two different cases. First case in which spring balance is present in an elevator which is going up with acceleration A, Now if we look at all the forces, mg will be down, T will be up. So what equation will be coming? F net equals to ma. If we apply, T minus mg is equals to ma. So T becomes, that is tension, is m of g plus A. So reading, what will be our reading coming? Reading will be m of g plus A by g. Reading is more as compared to when it was stationary. Let's consider the situation when your elevator is going down with acceleration A. Again, mg downward, downward, tension upward. What equation we will get? Because it is having acceleration downward, our F net equals to ma equation will be mg minus T is equals to ma. So T value comes out mg minus ma, which is m of g minus A. So reading comes out m of g minus A by g. Now again, as you can see, when the lift is going up, when the elevator is going up with acceleration, the reading is more. That means the block, or it will be appearing heavier, whereas when it is going down with some acceleration, the block will appear lighter, right? So this is all about your spring balance. Let us move ahead to combination of springs. Okay, next we are taking a look at spring, some basics of spring. So spring, if we talk about, let's consider we have a spring having spring constant K and it is of natural length L. Now whenever a spring is cut, let's say a spring is cut into two parts which has length L1 and L2. So their spring constant will not be K and K. Some students keep this confusion in mind that spring constant will be K and K. What is the condition? The condition is that the product of spring constant into length will be constant. The product of spring constant and length will be constant. So over here, if we say that this one has spring constant K1 and this one has spring constant K2, then it will be K1 will be written as, because the product remains same, so K1 L1 will be equals to K into L. So what can we write? K1 is equals to KL by L1. Similarly, for this one, we can write down spring constant for second, that is K2 will be KL by L2, right? This is when the spring is cut, how we find out the spring constant for the parts. Now, if I'm talking over here, combination of springs, if let's suppose you have been given two springs which are having spring constant K1 and K2 and they are combined in series. If we replace them with a single spring having spring constant K equivalent, so what can we write? K equivalent, the result is given as 1 by K equivalent is equals to 1 by K1 plus 1 by K2. This is our result, right? This is our result. Next, if we see, let's suppose two springs are there which are in parallel, having spring constant K1 and K2. If they are replaced with a single spring, then its spring constant, which we equivalent spring constant will be, K equivalent will be K1 plus K2. Now, it's easy to remember because in our minds we have resistance results very clearly in our minds. So for series, when springs are connected in series, the result is same as resistors in parallel. When springs are connected in parallel, your result is same as resistors in series. So that is how you can keep these results in mind. These are the results which are used a lot in your SHM chapter. Many a times to find out the time period your SHM is, in SHM these results are used. Okay, let us look at our next and the last topic, which is your pseudo force. So let us take a look at the concept of pseudo force, right? I have considered a situation over here. With the help of this situation, we will understand pseudo force. What situation we have? On a platform, a block of mass m is kept, and on the same platform, a person A is standing. He is at rest. A person A is standing on a platform where a block of mass m is kept. Now, near to this on the track, a train is moving with the acceleration of A. In this train, a person is there. Let's say that this person is B. Now, let us take a look at the block from observer A, that means with person A, and observer B, that is person B. So when person A will look at the block, he will feel that the block is at rest. As block is at rest, because acceleration of this, he is at rest, acceleration is 0, so with respect to him the block is at rest. Fine, no issue. So for observer A, block at rest, block at rest, well and good. Next, when observer B will look at this, for observer B, the block will be appearing to going backward. You know, when you have sat inside a tree, sorry, you will not sit inside a tree. When you have sat inside a train, it will appear as if the your trees are going backward direction. The trees are going backward direction. But actually, who is moving? The train is moving, and we who are sitting inside the train are moving ahead. So therefore, to this person who is sitting inside the train, it will appear as if the block is going backward with the acceleration of A. Right? Now, as we know that without your force, acceleration cannot be there. So for observer B, block moves with acceleration A in backward direction. And as we know that without force, your acceleration cannot be there. And because with respect to this B, there is an acceleration in backward direction. Therefore, to satisfy the condition of Newton's second law, that is F net equals to ma, we bring a force over here, this force, a force over here, F pseudo. The meaning of pseudo is fake. There is no force acting on the block in backward direction. But just for this observer B, it will appear as if the force is acting in backward direction, and due to that pseudo force, fake force, it's false force. So due to that force, there is an acceleration in backward direction. And how much is the magnitude of this pseudo force? Force pseudo magnitude will be mass of the block into acceleration of the observer. This A is acceleration of observer, or we also say that acceleration of the accelerated frame. Right? Acceleration of the accelerated frame or acceleration of the accelerated observer. This is your pseudo force magnitude. If we talk about direction is opposite to the accelerated frame. If acceleration is forward on the block, your force will be in backward direction. So this is all about your pseudo force. Over here, the person who is standing, whose acceleration is 0, they are this type of frame, these type of reference frame from where we are observing the reference frame, the observer whose acceleration is 0, these type of reference frame are termed as inertial frames. These type of reference frames are termed as inertial frame. Whereas the observer B is accelerating, he is the observer who is accelerating. These type of reference frame are termed as non-inertial reference frames. So this is all about your pseudo force. Now pseudo force many a times help us in dealing with the questions easily. I will take one of the questions, right? Before that, I will summarize all of this what I have discussed, because many students have a lot of confusion in this pseudo force concept. So I have discussed this in detail over here, right? I hope this point is clear. Again, I will summarize it. Whenever you are looking at an object from an accelerated frame, whenever an observer is looking at an object from an accelerated frame, with respect to this observer, a force, a pseudo force, a fake force is applied in backward direction, and that force, the pseudo force magnitude, is mass of the object into acceleration of the observer. Simple story. Many a times in many questions, this pseudo force help us in dealing with the situation easily. Let us take a look at it, one of the situation. Okay, so the situation to understand this application of pseudo force I have taken is, let's consider a trolley is there which is moving with the acceleration A, and in this trolley a bob of mass m is hanging with the help of a string, and when it moves ahead with acceleration A, this bob or this string makes an angle of theta. Right? Now we want to find out your tension or relation between theta and acceleration. So let us see how to deal with it. We will be doing it with the help of pseudo force. For pseudo force, let's say that the observer is standing inside the trolley itself. The observer is present inside the trolley itself. Now this observer is inside a accelerating frame. He is in a accelerating. This trolley is moving with A, so observer also moves with acceleration A. That means it's a non-inertial frame. So when this observer, which is a non-inertial frame, acceleration is not equals to 0. When this observer will look at the bob, what all forces for him it will appear. So first of all, tension will be there along the length of string, mg will be acting downward, and also because this observer is accelerating and when he looks at the bob, ma in backward direction will act. This ma is the pseudo force. This ma is the pseudo force. Now with respect to this observer, the bob is hanging over here at an angle theta. That means it is static equilibrium with respect to this observer. With respect to this observer, the bob is in static equilibrium. What is condition for static equilibrium? F net equals to 0. So let us apply it. First of all, we brought your pseudo force with respect to this observer. Whenever we write down equation with respect to accelerating observer, we applied pseudo force over here. Fine. Now let us see. So this is tension T. If this angle is theta, this angle will also be theta. So we can write down, if we do the resultant of tension, T sine theta, and this will be T cos theta, right? Let us write down the force. Let us balance the force. Static equilibrium condition if we apply, in y direction we can write down T cos theta is equals to mg. In x direction if we write down T sine theta is equals to m into a. This is with respect to observer, we are writing the equations. Fine. T sine theta equals to ma, T cos theta equals to mg. Equation 1, equation 2. To find out relation between acceleration and theta, if we divide 1 by 2, if we do 1 by 2, what we'll get? T and T will cancel. Sine theta by cos theta is tan theta. Tan theta is equals to A by G. Therefore, we can write down acceleration is equals to G tan theta in this case, right? Second, if let's suppose we want to find out tension. So for tension, what can we do? Equation 1, equation 2. If we square both the equations and then add them, T square sine square theta, T square cos square theta, sine square theta, cos square theta, T square comes common, it becomes 1. So we will get tension as T will be equals to m of root over A square plus G square. This will be the result for tension will be coming in this case, right? So this question, this situation we have solved using our pseudo force concept, right? So with this we have completed our video. All the concepts we have discussed, all the important concepts and applications we have taken a look for Newton's laws of motion. I hope you found the video helpful. It will be helpful for you in the coming exam, right? If you liked it, do consider to press the like button. Thank you very much. Bye bye.